This video we're going to be looking at the center of mass, or the centroid, of a planar lamina. In the last video we looked at finding the mass of such a thing, which a planar lamina, remember, was like a thin plate, you might say, of negligible thickness, and like maybe it's made out of plastic or metal or something. Okay, so before we talk about that, let's talk about what we would mean by a center of mass in general. And let's start with the simplest case where we have point masses placed on, say, a line, a number line. And it's the balance point for the masses. Depends on the size of the mass and the distance from the origin. So what we do is we take the mass times its x-coordinate, and then we do that for each point and then add those up. Okay, and then we divide that by the total mass of all of them added together. So it's each mass sub I times the x-coordinate x sub I. Add those up. That's the numerator, and the denominator is the sum of the masses. So what this does is it gives us a weighted average. This is exactly what we would mean by the mean or center of mass or centroid here. So it's the weighted average of these numbers. So it's like we had 11 values of 18 here, 9 values of 12, or a value of 12 weighted with a weight of mass of 9, and so forth. And we were to average those out. This is a weighted average of this. And this turns out to be the same thing as adding together, for example, 6 negative 2's, 9 2's, 8 4's, 9 12's, and 11 18's, and then adding those up and divided by how many we have and getting an average that way. It turns out to be equivalent to that. So it's a weighted average. And so just like in statistics, whenever you call this the mean, you use a x bar to denote that, and that's the centroid there. It's also a balance point. So if you think of this as like a lever, or on the playground we might have called these a seesaw or a teeter-totter. This is the fulcrum right here where it balances. Now we consider the plank here has no mass at all, but then we put weights on there at these places, and then if we put the fulcrum right here at 8, then it will be perfectly balanced. So it's the center of mass or balance point. Okay, and that's how we figure it out. Let me show you something kind of interesting with this GeoGebra sketch here. So if I do, should be able to go to this. Let's see here. Okay, and now we have this this one here. We can move these masses around. Notice right now this one's really large, and so it's balancing a lot of stuff that's over here, and so that pulls this mean, this balance point really close to that. So if we pull this down closer to the others, say at 11, now the average or center of mass is much further over here. And you can see what happens if we move a point here to the right, the center of mass gets moved with it. But also if we make a point heavier and increase its mass, say mass 1, say we increase this from 6 to 10, that's going to pull the center of mass that direction as well. Whereas if we decrease it, like say down to 2, that'll pull the center of mass back to the right. So it's a matter of their location and their size, their mass, is going to determine where this balance point is. And you can see the calculation down there. Well, if we go to 2 dimensions, like we're always doing in this class, extend the dimensions, then this idea looks something like this, where we have some point masses. These are 3 of these here, and the size of the red circle is sort of indicating the size of the mass, but we're considering it all located at a single point. Then our center of mass actually is at the end of this vector right here, right there, and that's the balance point if we were to balance out, if we were to connect these up with maybe some kind of wireframe where the wires didn't have any mass. That would be the balance point right there. And again, it depends on the size of these masses and their locations. And this formula that we had, summing the masses times the x-coordinates and then dividing that by the sum of all the masses, that generalizes real nicely to find the y-coordinate as well. It still works the same for the x-coordinate in this 2D case, but then the y-coordinate of the centroid, the y-bar, is found pretty much the same way. You just take the masses times the y-coordinates and add those up and divide by the sum of the masses. Okay, and in fact, this would generalize to 3 dimensions. You could find z-bar to be the sum of the masses times the z-coordinate divided by the sum of the masses, or however many dimensions you might have. Again, in this GeoGebra sketch, we can kind of see a little bit what happens as we move a mass around. As we move this to the right, the centroid goes to the right. As we move it down, the centroid moves down. As we change their masses, this mass is to the right and below the centroid, so increasing its mass is going to move the centroid further to the right and further down. Oops, wrong one. B. Further to the right and further down as we pull that mass bigger. As we go smaller, it's going to be pulled a little bit toward the other point masses. If we increase A, that centroid is going to be moved toward A as we increase the mass of A. As we increase the mass of B, the centroid is pulled toward B. As we decrease B's mass, it's pulled away from B. And we can see the effect here of choosing different locations and different sizes for the masses. And of course, this is just with three things here. So I thought those things would be useful for us to kind of get the idea of what we're talking about. So now how do we do this for a planar lamina? So suppose we have a little region, a lamina, some sort of flat region, and we want to know the mass of that. We already said we can just integrate the density function there, so it could have a variable density. We did that in the last video. Now how will we find the centroid? Well, the bottom here is like the total mass. That's going to be like what we did last time. And it turns out the top is going to be an integral as well. So to see that, suppose we have some sort of lamina that maybe looks like this. The way we can kind of relate it to what we just did is we can approximate this centroid by breaking this up into little bitty squares. So let's say if we use the squares that are on the grid, or it doesn't have to be squares, it could be rectangles, and then look at each one of those separately. If we assume that this little square piece is replaced by a point mass right in the middle of that region, so or at least somewhere in the region, we have a density right there at that particular point times the area of that region. Remember, that density is a density per square unit times the square units for the area, gives us a mass for that little slice, or at least an approximation of that mass. And then we can say it happens right at that one point. So now we've reduced it to a situation that we saw on the previous slide, where we have a bunch of point masses and we proceed to work it like before. Okay? And the numerator here from what we were looking at before is the sum of the masses times the x values for the x bar. Well, so what we do is we take that, if you look at the second line here, we take the sum of the masses. Well, to get the mass, we take the density at that point times the area of that little rectangle. Then we multiply it by the x values. That's the x times that mass for that one piece. Then we sum those up for all the little subrectangles, and then take a limit as the n goes to infinity and the delta a sub k's go to 0, and that becomes a double integral. It's a double integral over whatever this domain is, D, whatever that region is. The x sub k just becomes x. That's just delta of xy. And of course, delta a sub k becomes dA in our notation here. The sum here is actually a double integral here. And so this is called the moment about the y-axis. So if you think back to here, we're actually considering what's happening centered at 0. So what's going to happen is we put these masses to the right of 0. It's going to want the right side to go down. Going to push the right side down. If you go to the left of 0, those masses are going to have a tendency to push the left side down. Left and right of, well, say of 0. Okay? And then so this numerator has something to do with the tendency to make this fulcrum want to rotate or push down on one side or the other of 0. Well, when you go to the two-dimensional case, you're going to get a similar thing here. The x, you take this part here, it's going to have a tendency, all three of these in fact, are on the right side of the origin, well, the right side of the y-axis, and they're going to have a tendency to push the plane down. If we would have kept the plane rigid, but then rotate it, this would rotate it about the y-axis. It would push it in the sort of downward direction over here on the right. Whereas if we say move this one over, so if we move a weight over here, a mass over here, say to the left of the y-axis, say if we move enough of these weights over here, now this has a tendency to push down on this side of the graph. So this part in the second and fourth quadrants is going to be pushing down more than the part over here on the first and fourth quadrants. So the center of mass is got a negative x coordinate. That's going to make this plane have a tendency to rotate about the y-axis, with this part over here to the left going down and this part over here to the right coming up. So rotating around in that direction around the y-axis. So notice it's the y-axis that this thing is having a tendency to rotate around. If we put more of the masses over here, particularly it's not necessarily exactly the masses, it's the product of the mass and the x distance from the x-axis. There may be a place right in here somewhere where I can get it just right and get that balance to happen so that it's 0 here on the x-coordinate. That means there's an equal amount on both sides of the y-axis. So this is going to be stable and not want to rotate in that direction. Okay, does that make sense? Hopefully that makes sense to you a little bit. So in any event, we're talking about measuring how it's rotating about the y-axis. So this one that has the x in there is the moment about the y-axis, whereas the one with the y in is the moment about the x-axis. When we think about their distances from the x-axis, which are y values, multiply those by the density and the area, and sum those up and take a limit. That's a double integral. That's going to be the tendency to rotate about the x-axis. We have that. And then to find x bar, you use the one that has the x in it, which is the moment about the y, and divide that by the mass, total mass, which is given by the integral here, which should not have an x in it. Okay, and so if you're just integrating the density dA, then you get the mass, total mass. If you put an x times that density and integrate it, you're getting what's called the moment about the y, or the first moment about y, or the moment about the y-axis. And if you want to find the moment about the x-axis, you put the y times the density and integrate. To find x bar, you take the integral with the x times the delta dA and divide by just the integral of the delta. In other words, you moment about y divided by m. And the moment about x divided by m is the y bar. So ultimately, here are your formulas that we have for the mass, total mass, the two moments, and then the centroid, x and y coordinates of the centroid. So let's look at an example that we looked at in our previous video, where we had this region right here. It was bounded above by 9 minus x, and below by y equals 2x, and then on the left by x equals 0. And so we've got this triangular planar lamina. And the density depends on x. It's actually x plus 3. And we found that we could find the mass by just integrating the density function dA. The density function was x plus 3. We described this region as going from 2x on the bottom to 9 minus x on the top. Those are y values. So we integrate with respect to y first, and then finally with respect to x, where x goes from 0 to 3. In our last video, we worked that out in detail and found that that was 54 kilograms. Okay, now let's find the moments. Set up the integrals from the moments about the y and x axes. See if you can do that yourself. Come back when you got it done. Press pause now. Well, all we have to do is take this integral for the density and just stick an x in front of it right there, not in front of the whole integral, but in front of the integrand, multiplied by the whole integrand, and that's your moment about y. And take the same thing, but instead of the x, put the y. That's the moment about x. All right, let's see if we can work these out. It may take a little bit of time because these are double integrals. It may take a little bit of time to work them out, but work these out yourself if you can, and then come back and check your answer. Press pause now. All right, well, here they are worked out. Let's see if we can chase through the details. Let's do the one on the left first. The moment about y has the x in it, and that's used to find the x coordinate of the centroid. All right, I'm going to distribute the x first, and I've got x squared plus 3x. Okay, and then I'm going to factor it out front of that first integral because it doesn't have any y's in it. So then we're just integrating dy with respect to y is just y. We should still have that term there. Okay, and then the y is evaluated from 2x to 9 minus x. You put in the 9 minus x minus the 2x. Let's see, that's minus x minus 2x is minus 3x. Now we're going to multiply these two guys with FOIL. Multiply them out. Let's see, 9x squared. Let's do, first times first. 9x squared, and then you multiply last times last is minus 9x squared. So those cancel. What's left? Let's see. We've got a 9 times 3x, that's 27x, and an x squared times negative 3x is negative 3x cubed. Okay, so there we go. Add 1 to the powers, divide by the new power because we're integrating with respect to x this time. So power goes up to 4, divide by 4 makes that negative 3/4 for the coefficient. That x becomes x squared, divide the coefficient by 2, it becomes 27 halves. So our antiderivative is negative 3/4 x to the 4th plus 27/2 x squared. Evaluate by plugging in 3 and 0. Where there's an x, plug in a 3. Minus, where there's an x, plug in a 0. All right, let's see what we got here. 3 to the 4th is 81 times negative 3 is negative 243, and that's still over the 4. 3 squared is 9 times 27 is 243. That's still over the half. And these two turn out to be 0. Get a common denominator of 4 by multiplying the second fraction by 2 over 2. That's 486 fourths minus 243 fourths is 243 fourths, or exactly 60.75. I checked that with a calculator, graphing calculator, actually not just a graphing calculator, but a CAS calculator up here, and it does turn out the same. Okay, a little bit harder on the next one over here, but not a lot. Replace, instead of the x here in the front, we have a y times that density. So there's our integral. And again, we can pull the x plus 3 out, but this time we're integrating y. So this is 1/2 y squared. 1/2 I can bring out, in fact, all the way out front of the integral, because it's a constant. And I've just got y squared evaluated from 2x to 9 minus x. So that's 9 minus x quantity squared minus 2x quantity squared. All right, square this out. Let's see, we get squared in the last term, that's x squared, multiply and double for the middle term, negative 18x, and square the first term, that's 81. That 2x squared is 4x squared, and that's minus because of that negative sign, subtraction sign there. Negative 4x squared plus x squared is negative 3x squared, and I can factor out a negative 3 out of this. So that makes right out front with the 1/2, makes a negative 3/2 out front. And I'm dividing all these by negative 3. That gives me 1x squared plus 6x minus 27. Then I have to do some long multiplication here to multiply these out. I did it on scratch paper, but I don't have it here. Multiply the x times each term, multiply the 3 by each term, combine like terms. X times x is x cubed, 3 times negative 27 is negative 81. For the x term, we're going to get a 3 times 6x, that's 18x, and then minus 27x by multiplying these two is negative 9x. And for the x squared term, we get 3x squared from these two, and 6x times x is 6x squared, and 3x squared, that's 9x squared. So anyway, we get this here. Now it's a polynomial, pretty simple. Add 1 to the power, divide by the new power, so that's 1/4 x to the 4th. Power goes up to 3, divide the 9 by 3 is 3. Power goes up to 2, divide the coefficient by 2, it's negative 9/2 x squared for that term. And of course, constant terms just pick up a variable of x. I'm going to evaluate from 0 to 3. You know what? I want to get rid of these fractions first. So I'm going to factor out a 1/4 first. Along with this negative 3/2, that puts negative 3/8 out front. All right, so I'm dividing all these by 1/4 or multiplying by 4. So that coefficient is 1, that's 12. That's 4 and a 2 cancels, negative 18 for that coefficient, and 4 times negative 81 is negative 324. That allows me to get the fractions out, not have to mess with fractions on the next part. It's equivalent to finding a common denominator at the end. So what's left? I take all these things and put in a 3 minus, put in a 0. Parentheses minus parentheses. First parentheses, plug in 3 in the function. Second parentheses, plug in our lower limit 0. All right, we still got negative 3/8 times the whole thing though. 3 to the 4th is 81. 3 cubed is 27 times 12 is 324. 3 squared is 9 times negative 18 is negative 162. 3 times negative 324 is negative 972, and all the rest of the terms are 0. Add all those whole numbers together, or integers together, and you get negative 729. Multiply by negative 3/8, you get positive 2,187 over 8, or exactly 273.375, and that's what I get with the calculator as well, so that's good news. All right, now go ahead and use these to find the coordinates of the centroid. Press pause. Come back when you're done. Okay, here's the answer. We know the mass we saw earlier was 54 kilograms. Okay, we know this is the integral for the x and y axes that we have here. This is the values that we just found. So here's what we have. 54 kilograms for the mass, 60.75 for the moment about y, 273.75 for the moment about x. The x bar is just the moment about y, the one that has x in it there, and that's 60.75 divided by that 54 here. And then the same thing here, divided by the 54. I guess technically the units of these moments are kilogram meters divided by kilograms. These are just meters. These are just locations in our plane here. It's the same coordinates. Same. The x bar is going to have the same units as x, and the y bar is going to have the same units as y when the dust settles. And then similarly for y bar, you take the moment about the x-axis, which is the one that has the y in it here, 273.75. 273.375. Let me see. And yeah, 273.375, and divide that by 54, and you get this. As a fraction, that's 9/8, 81/16. In decimals, that's 1.125, 5.0625. And here is that centroid graph. Now, it should make sense. Since this is a convex region, we should see the centroid in the region somewhere. Sometimes it could be outside the region if you have a concave region. But here we go. Here it is. Let's see if this sort of makes some sense. Okay, why would this be the balance point? And that's what it should be. It should be, if this was our little plate, if we were to balance this, say on the tip of a pencil or something, that should be the exact point. If we could find that exact point, and just we should be able to balance the plate on there. Does this make sense? Well, certainly it's within our region, which makes sense here. The density, notice, is getting bigger as it goes to the right, but up and down it's the same density. So that this means up and down, the area above this point, we drew a horizontal line there, should match the area below that, because they should balance out, because the density is uniform in the XY. Well, actually that's not necessarily true, because it is changing from the right to left. Okay, but it should be, yeah, it looks like that's reasonable, because it's going to be somewhat in the center here. Okay, this part, even though it's smaller over here in area, it's going to be a little denser. So this is going to have a tendency to pull the centroid up and to the right of what it would be if this was a uniform density. So if it's uniform density, we'd expect it to be a little further to the left, probably. Okay, but that seems like a reasonable place for it to be. Let's look at one more example. This is another example that we looked at in our last video, and this is a planar lamina. The density is given by x plus 2y, and that's in kilograms per square meter. So it's an area density, and it's bounded by curves y equals 2 to the x power. That's the green curve here on the bottom, and above by y equals -3/4 x minus 2 squared plus 4. Which we saw another way to write that if we expand it out is by this polynomial, -3/4 x squared plus 3x plus 1. That's the curve on the top. And if we put a vertical strip, it goes from the bottom, the exponential, to the top, that quadratic, and those are y values, so we integrate with respect to y first, put in our density function here, then we integrate from x going from 0 to 2, which are our boundary points there, and we saw in a previous video, we got this. We did have to integrate by parts once as part of this problem. But anyway, there's the exact value, or approximately 10.5. Okay, now see if we can find the moment, or at least set up the appropriate integrals for the moments. Well, setting up the integrals for the moments is pretty easy if you've already got the one for the density, because you just take the density integral and just put in an extra factor of x here, and that gives you the moment about y. And put in the density formula and put in an extra factor of y right there for your integrand, and that's the moment about x. So setting up the integrals is pretty easy once you got the density function set up. Now evaluating these is a little bit of work, and I'm not going to work out the details here. I'm going to kind of cheat and let a calculator work for me here, because this is going to involve. It's really not any not a lot harder than figuring out the mass formula. This is the mass formula here, but this one for figuring out these moments is very similar. It does involve a longer process. It does involve integration by parts, maybe even more so than we did before. And but in any event, here's the exact value which I was able to find from the graphing calculator. I do need to fix this up here. In fact, let's back up to this slide here. This should have an x right here and a y right here, which is where that came from there. Just correcting that slide. And then same thing here and here, but of course I did it correctly here, so we're good to go on my answers. This calculation here tells us this is the exact answer, or approximately 11.99077 whatever. Divide that by that mass, and this is going to be the x bar, at least approximately. So about 1.14 for the x bar. Similarly, to find y bar, we do the moment about the x-axis, which has the y in it right here. Again, very similar types of skills in working out these two antiderivatives. But when we evaluate at the end, we get this value exactly, and there is the decimal approximation. And again, I use the CAS calculator to actually do that. And once we got that answer, then we want to divide that by this mass over here, and to get our approximation for our centroid. If we were to graph that, here it is graphed here. It's about 1.14, 2.83, which you can see that's where I have this point here, and that should seem like a reasonable place for the boundary point. You notice it is a little closer to this upper right corner than it is, say, down here to the lower left, and that's because it's getting a little more dense as we go to the right and up. So even though there's a little bit less area up here than there is down here, the density is a little higher up in this part than it is down in this part down to the lower left. But in any event, there's the centroid. If you got something that's way outside your region, then you need to really think carefully about that to see if that even makes any sense. In fact, it probably doesn't make any sense if you've got a convex region. So just kind of see when you're done if your values make any sense at all. So that's how we find the center of mass of a planar lamina.